Now, I would like to start the lecture of the mathematical treatment of particle size distributions. In this lecture, we assume that the particles are spherical and consider the diameter as the size. In powder technology and multiphase flow, how to represent the geometric properties of particles such as the mean size and the size variation is very important. The mathematical treatment for those matters is established. The whole lecture consists of part 1 and part 2. This video is part 1. This page shows a brief content of part 1 and part 2. Part 1 describes how to treat particle size distributions. At the beginning, the lecture is given in the order of probability, probability density, and probability density function. After that, probability density function based on particle number, particle surface area, and particle mass will follow. At the end of part 1, I explained the delta mean diameter D32 and the specific surface. Part 2 begins with cumulative distribution. In the field of powders and particles, size symbol D is often accompanied by a subscripted number. The delta mean diameter D32 is one example. Besides the delta diameter, there are some examples such as D50, D84, D16, D36.8. These numbers are related to the cumulative distribution. I will try to let you understand the meaning of these numbers. Then I will explain the normal distribution, log normal distribution, Rosen random distributions, and their probability papers. The background knowledge of this lecture is elementary calculus, but for part 2, you should know exponential and logarithmic functions to some extent. For those who are not good at probability, I will start at the beginner's level. This page prepares the formulation of the size distribution. Let's consider a collection of particles of various sizes as shown in the figure. The total number of particles is large M. All particles have their own sizes, D1, D2, etc. In this lecture, the capital letter M is used also for particle numbering. Individual particle sizes are accompanied by subscript numbers with parentheses. The particle mean size mu is defined by dividing the total of individual part size by the total number m. This is the most familiar definition of mean size. However, when the number of particles becomes huge, we have to resort to another formula using probability. Before considering probabilities, let's group the particles in the order of size range. The width of size range is each group is delta D. The number of groups is L, large L. In this lecture, the capital letter L is used also for group numbering. each group has a representative size, D1, D2, and so on. Particle sizes of groups are accompanied by subscripted numbers. The representative size is the size of the center. The DI group contains particles with size ranging from D1 minus half delta D to DI plus half delta D. Let's assume in the following formulation that all particles in the same group have the same representative size. In the next page, I will derive the equation of mean size by using this assumption. In this page and the next page, I will explain how the size distribution histogram developed into probability density and probability density function. The horizontal axis represents the particle size, and the vertical axis represents the number of particles. The familiar definition of mean size is shown again. The representative size multiplied by the number of particles of a group approximately gives the total of particle size of a group. That is, DI cross delta NI is the total of the particle size of the DI group. So the numerator of the first equation can be replaced by the second equation. This equation is further transformed. Delta N1 over N, delta Ni over N, etc. appear on the right-hand side of the third equation. Delta Ni over N is the probability that the size D takes a value from Di minus half delta D plus up to Di plus half delta D. The numerical value of this probability depends on the value of delta D. To remove the influence of delta D, the probability are divided by delta D. In that way, the probability density FD1, FDI, FDL are defined as shown in the bottom row. Let's move on to the next page. In this page, I will explain the conversion from the probability density to the probability density function. Let's substitute the probability density FD1, FDI, etc. into equation 1. As a result, mu can be expressed by equation 2. Let's change the form of equation 2 to the expression using the summation symbol sigma. Furthermore, taking the limit of delta D infinitesimal, equation 2 can be expressed in the integral form of a continuous function. Fdi is the probability density. The continuous function Fd is probability density function or frequency distribution function. Under the dotted line, the sum of particle numbers delta N1, delta N2, etc. is equal to the total number N of all particles. If we use the probability density Fdi, equation 4 becomes equation 5. Taking the limit, equation 5 becomes equation 6. Equation 6 indicates that the integral of Fd over the entire domain is unity. Such a function is called normalized function. Next, I will show the formula for averaging a function of size d. Yd is any function of d. To find the mean of yd, it's enough to put yd before the probability density function of d and carry out the integration as shown by equation 1. As an example, consider the particle mass. Mass is the function of d as shown in equation 2. Substituting equation 2 into equation 1 gives the mean of yd, that is the mean mass as shown in equation 3. Besides the expression based on the probability density function, the mean mass is simply defined as the total mass m divided by the total number n of all particles. The integrand times delta dd can be expressed as dm over n, and so we have equation 4. The last part of equation 3 is shown below equation 4. Dividing equation 4 by equation 3 gives dm over m in equation 5 as shown on the left. So far, I have explained only the number-based probability density function. After this page, probability density functions other than number-based will be explained. They are mass-based functions, mass-based and or area-based distribution functions. Therefore, in order to distinguish the number-based function from other based functions, the subscript 0 is attached to the number-based function fd as shown in equation 6. Next, we will consider the mass-based distribution. As before, the number of all particles is given by equation m. All particles have their own mass, m1, mk, mn, etc. The following transformation of the formula is basically the same as for the number-based distribution. The symbol m is defined as the total mass of all particles. Regarding the size grouping, it's the same for both the mass-based and number-based distributions. The only difference is that particle numbers are dependent variables in the number-based distribution, while the particle masses delta m1, delta m2, delta mi, etc. are the dependent variables in the mass-based distribution. In the following pages, I will derive the equation of the mean size from the sum of the particle mass of each group. As in the case of the number-based distribution, I will show a histogram for the explanation. The horizontal axis represents the particle size. The vertical axis represents the particle mass. Delta D is the width of the particle size variation in each group. The particle mass of D1 group is delta M1. The particle mass of DI group is delta MI, and so on. The mass-based mean size mu is given by the equation by the first equation. Di times delta mi for each group are summed over all groups. The mean size mu is obtained by dividing that summation by the total mass m. Transforming the first equation, we get a second equation on the same line, which contains delta m1 over m, delta mi over m, etc. on the right-hand side. The equation number of this second equation is 1. Please remember this equation 1, for which will appear in the next page. Delta mi over m is the probability that the particle size d takes a value from di minus half delta d to di plus half delta d. The numerical value of probability depends on the value of delta d. To remove the influence of delta d, the probability are divided by delta d, and the probability density fd1, fdi, the fdl are defined as shown in the bottom row. This logic is the same as for the case of number-based distribution. The superscript 3 is attached to fd to show its mass-based distribution. The number 3 is because mass is a three-dimensional quantity. Equation 1 of the mean size mu3 is shown again. Let's substitute the probability density fd1, fdi, etc. into equation 1. As a result, mu3 is expressed by equation 2. Let's change the form of equation 2 to the expression using the summation symbol sigma. Furthermore, taking the limit of delta d infinitesimal, equation 2 can be expressed in the integral form of a continuous function. F3 di is the probability density. The continuous function f3d is the probability density function or frequency distribution function. Under the dotted line, the sum of the mass of individual part groups d1, d2, etc. is shown to be equal to the total mass of all particles. This relationship corresponds to the result that the mass-based probability density function f3 is a normalized function. This page compared the number-based, mass-based, and area-based distributions using histograms and equations. The superscript 0, 3, and 2 are attached to the mean size symbol mu and the probability density f. I have already explained the number-based and mass-based mean size in detail. Also, I will not explain them any further. The area-based mean is displayed at the bottom. The area-based mean plays an important role when dealing with phenomena such as absorption. You can derive the area-based formulation by replacing mass with surface area. So the explanation of the area-based distribution is also omitted here. The mass-based mean particle size mu3 is shown in the discrete form and in integral form. You can put d dot dm over m equal to the integrand d dot fd times dd. The symbols d on both sides cancel out each other. Then dm over m is expressed by the equation on the second line. I have shown before that dm over m has been expressed by using the number-based distribution function f0. So if you forget it, please back to the page 5 and refer to equation 5 on that page. The equation on the third line is the one obtained before. From these two equations, the relationship between the mass-based distribution function f3d and the number-based distribution function f0d is obtained. From here, I will compare various probability density functions in the graph. First, the number-based distribution f0 is shown. Next, the mass-based distribution f3 is shown. You can see the position of peak shift significantly to the right. Between the number-based and mass-based distribution are the length-based and area-based distributions. All of the mass-based, area-based, and length-based distribution functions are expressed by the number-based distribution function. I omit the derivation of the area-based and length-based formula. Please check for yourself. The particle size that gives the highest frequency is called the modal diameter. As you have noticed, there are different frequency distributions defined for particle size. Note that the mean diameter, the mode diameter differ depending on which frequency distribution f is used. Next, I will explain the specific surface because it's closely related to the area-based mean size. The specific surface is defined as the surface area per unit mass of particles. Its unit is square centimeter over gram. The surface area is more important than the size and the mass in absorption phenomena of particles with complicated shapes. Measurement of particle surface area is not performed on individual particles, but performed collectively for many particles. Gas absorption techniques are used for that purpose. There are various kinds of surface area, such as the particle outer area, the area of irregularity on the particle surface, the area including cracks, and the area including the area of the pores penetrating into the inside of the particle. When only the outer area of the particle is considered, The specific surface SM can be calculated by the formula written here. Let's consider the specific surface of 1 millimeter particle and 1 micrometer particle with a density of 1 gram over cubic centimeter. The specific surface of 1 millimeter particle is 60 square centimeter over gram, and that of 1 micrometer particle is 60,000 square centimeter over gram. This is the last page of part 1. In droplet absorption phenomena, the delta mean particle size D32 is often used. The delta mean size D32 is the mean size defined by the area-based distribution function F2. If we rewrite F2 using the number-based distribution F0, you can write the delta mean size D32 like this. The numerator integrand contains D cubed, and the denominator integrand contains D squared. So the symbol for delta mean particle size is expressed as D32 or D32. Transforming the right-hand side of the equation for mean size D32 gives the relationship between the delta mean diameter D32 and the specific surface area SM. This concludes part 1 of my lecture. Thank you.